So extremal graph theory. Okay. And this is my topic of research. This is what I work in. So I thought it'd be fun to sort of end with this and a couple of my favorite theorems. So the idea of extremal graph theory is you fix a parameter in a graph. So we've learned all these different parameters in graph. We learned about the chromatic number. We've learned about the maximum degree. We've learned about minimum degree, about clique number, about independence number, all these different measurements you can take for a graph. And the rough idea in extremal graph theory is to say, okay, what if I fixed one of these parameters and say, I don't want my independent sets to be too large, or I don't want my clique number to be too large, something like that. So you say one of these parameters is fixed and can't be too large. What's the property of the other parameter? So some other parameter. So you fix two. How does one control the other? Okay. And we've seen like one really good example of this where they didn't have any effect on each other. And that was girth and chromatic number, right? We saw that awesome theorem of Erdős where they both could be big simultaneously. They somehow didn't affect one another, which is interesting in its own right, but some definitely do affect each other. Okay. And the one I want to talk about today and Monday is basically the clique number, and say I have a graph and it doesn't have cliques, it doesn't have complete graphs that are too large, right? We say no complete graphs of size larger than 10 or something like that. And the other parameter we're going to measure is the simplest, is how many edges are there in the graph. Okay, so let me just pose the question first, and we'll think about it a little bit, and then we'll prove one theorem here 3 or 4 times today. Okay, so how many edges can we have in a, what I'll write as triangle-free graph? Let me just make sure this is clear. By triangle-free graph, I mean a graph with no subgraph triangle. Okay, no triangle subgraph. Okay, a triangle is a complete graph. It's basically the smallest interesting complete graph. Yes, a single edge is a complete graph, but the number of edges in a graph with no edge is pretty uninteresting as a question. So we want to avoid triangles and figure out how many edges that you can have here. Okay. So what do I want to take? Yeah. Okay. So roughly, if you think about this for a little bit, it makes sense that there's some competing notion here, because as you put more and more edges into a graph, it gets harder and harder and harder to avoid certain configurations, a triangle in particular, right? Eventually, if you put in all the edges, you get a giant complete graph, and that obviously has triangles, has tons of triangles, so it definitely has a triangle. So like at some point when you add in edges, you're going to be like, oh, I can't avoid a triangle anymore. And the next edge adding is going to be a triangle. And one of the questions we want to talk about is, how big can you get? How many edges can you have and not have a triangle? Okay. So the first thing you do in problems of this type usually is try to come up with some kind of construction. Okay, come up with some graph that doesn't have triangles, that has a large amount of edges, just by attempting things, and see what you can come up with, right? We've seen this in homeworks and even exams where you ask a question, like the Hamiltonian cycle one. Give me a graph that doesn't have a Hamiltonian cycle, but still has like a lot of edges or has high minimum degree. That's an extremal question as well. Okay. Okay, so there's one other thing we have to fix here, though, is how many edges. This question is uninteresting unless you fix another parameter of the graph, say the number of vertices. Because I would just say, well, how many edges can you have? It's like, well, just take a tree on infinitely many vertices. It doesn't have any cycles, anything, and it has as many edges as you want. But that's not what we're looking for, right? That's boring. You got to fix the number of vertices or something else. So that'll almost always be the case. So how many edges can we have in a triangle-free n vertex graph? Okay, so the number of edges is going to depend on n. It's going to be a function of n. So what's one graph that we know, or one class of graphs that definitely doesn't have triangles in it? Yeah, Van, that's right. Trees don't have triangles because they don't have cycles at all. Unfortunately, trees are sparse, right? They really don't have a lot of edges. What's another category of graph that has more edges and still doesn't have a triangle? Yeah, Eric, good. Bipartite graphs, right? We can take any bipartite graph. Trees are also bipartite graphs. But if I take a bipartite graph, I'm going to draw it like this, say with classes A and B, this is triangle free, right? I mean, it has no odd cycles. We proved that theorem, but to see that there's no triangles is super easy, right? If there's a triangle, you have two vertices on one side, either two here or two here, and there's no edge inside of a class, okay? And if I want to have a lot of edges in a bipartite graph, what's the best thing to consider? Well, it might as well be a complete bipartite graph, like put all edges you can, right? Moreover, I drew A and B of different sizes here, but what's going to be your best option when A and B are as close together in size as possible? To prove that, that's a little bit of calculus, actually, right? Actually, calculus surprisingly comes up in extremal graph theory a lot, right? So the question is, the number of edges here. We're going to resolve this in a little bit anyway, but number of edges is the size of A times the size of B, which is maximized at when you have n over 2 floor times n over 2 ceiling. If n's even, they're just the same number as each other. If n is odd, you have a floor and a ceiling. And how do you actually solve this? Well, you solve it as follows. The size of A times the size of n minus A, right? We have n vertices. So I know that the two classes sum together is this quantity here. And then if you want to maximize A times n minus A, this is literally a calculus problem. You've done this one before. This is basically equivalent to those questions in calculus where it's like you have 100 yards of fencing and you want to create a maximized sized area with that amount of fence in a rectangle shape. How do you solve it? It's the same question. And actually, that question is extremal calculus. Like that's the same idea. You have a fixed parameter, length of fence, and an additional condition that it must be in a rectangle, and you want to maximize. You want to make an extremal version of something else. So these are just like questions we've seen in calculus applied to graph theory, basically. Okay, and in graph theory, they're much prettier, I think. But the concept is the same. It's a typical thing we do in combinatorics. Okay, so we came up with an example here, right? This n over 2 floor times n over 2 ceiling comes out to n squared over 4 floor. It's not that important, but if you just check the different odd and even combinations that you can have, it always equals this thing and squared over 4 floor if you take floor ceiling on n over 2. Okay, it's not that hard to check. So this is a reasonable guess for an answer. Maybe this is the most. Maybe this is the best construction, but maybe not. Maybe there's some other crazy thing you can build with more edges. Okay. And so the theorem we're going to prove, this is called Mantel's theorem. And this is ancient. It's from 1907. That's really old in graph theory. In fact, again, we've seen a few theorems of this type. This is older than graph theory itself. So he wasn't talking exactly about graphs in the way that we do. But he says that the maximum number of edges in an n vertex triangle free, it's a free graph, is n squared over 4 floor. Okay. Now, this theorem actually says something extra that we're not going to prove today. We'll prove on Monday, essentially. It says something more, and this is subtle here. It says the maximum number in a triangle-free graph is this quantity here. So notice that says both you can achieve this number and that you can't get higher than it. Okay, right? The max is literally is. But actually, Mantel's theorem also says something cool. It says that any graph achieving n squared over 4, so achieving this maximum, is this picture here. It's a complete bipartite graph. There's no other graph that looks different that achieves the same number of edges. Okay, so the construction is unique. There's only one example that achieves this maximum. Okay, which the statement of the theorem doesn't say that. We're not actually going to prove that today, but we'll prove a more general version of this theorem later, and in that we will prove the additional condition that the construction achieving the maximum is unique. Okay, that's actually very interesting, and it provides another way to prove the theorem as well. Okay, that's just a taste of what's to come on Monday. Okay, so today I want to prove this theorem. I think there's 6 or 8 different proofs of it floating around out there. We'll do 3, maybe 4, depending on how fast it goes. Okay, so proof 1. So one of my favorite things about extremal combinatorics is that there are tons of different proof techniques that have been developed here. And so I'm really interested in new proofs of existing theorems. That's a specific topic that's something I spend time researching. because you develop these new techniques and they can be used to prove new things as well, not just reproofs of old theorems. And the different proofs you understand, you start to get a deeper understanding of why this stuff's true too, right? We've definitely seen proofs in this class that are like, okay, it's true, it doesn't give me any insight, it's complete magic, and others that do give some insight, like you get a feel for why things work. Okay, and you'll have to judge these on their merits in that regard. But so the first is just induction on n, on the number of vertices. Okay, so the base case is actually, we need two base cases because we're going to drop the number of vertices by 2 at each step. But the base cases are n equals 1 and n equals 2, and I'm just going to say easy. Okay, but I mean, you can just check here what's going on. When n equals 1 and n equals 2, how many edges can you have and not have a triangle? Well, with one vertex, you just have no edges. And with two vertices, you can have 0 edges, or you can have 1 edge. That's the most you have. Obviously, those are both triangle free. And if you compare them against this quantity, you're fine. 1 and 2 squared divided by 4 floor. Wait a minute, something's fishy here. Oh, no, we're fine. We're fine. Sorry, it's squared. You get 4 over 4 floor, you get at most 1, and you achieve it. The other one gives you 0, which this has. Okay, so those are correct. And then actually, I mentioned that there's this stronger result that the graph is like uniquely this one. Both of these satisfy this as well. This is a bipartite graph that's balanced, right? I mean, it's not, yeah. So, okay, that's the base case. So now we're going to let n be greater than 0, greater than 2, and statement holds for smaller graphs. Okay, so any graph on n minus 1, n minus 2, n minus whatever vertices that's triangle free is its number of edges is bounded above by the appropriate, n minus whatever squared over 4 floor. Okay, so let's look at G is n vertex, triangle free, and let's look at an edge in that graph. Okay, and let xy be an edge of G. Okay, technically we have to know that an edge exists, but if there's no edge in the graph, then we have 0 edges, then the bound is satisfied, right? So there should be an edge. Okay, and let's draw this picture here. So here's my edge xy, and here's the rest of the graph. So I'm going to call this G minus xy here. Okay, so G minus xy is clearly triangle free, right? I remove the edge xy and whatever edges went across here, that can't create a cycle. I mean, this is a subgraph, obviously. And it has n minus 2 vertices, right? Because I pulled 2 vertices off from the edge. So induction says, let's call this, okay, let's just say, so induction says that inside of here, there's at most n minus 2 squared over 4 edges, right? Actually, I can put the floor on that, but this is a weaker bound, right? Like removing the floor, it still holds that it's at most that, okay? Yeah, keep in mind when you're counting edges, if you give an upper bound that's not an integer, you can always round it down because you can't have a non-integral number of edges. Okay, that's a common little trick in combinatorics that occasionally is very, very important. Here we kind of get it for free at the end. Okay, so I use this slightly weaker bound. Okay, now the key observation in this proof, and actually this will return to us a couple of times, is how many edges can you have going across here? So like these can send edges over here. And I want to count the total number of edges in this picture. I've counted all the edges inside of here. I need to count this edge, and I need to count the edges going across here. What can you tell me about these edges going across? What's an important observation about the collection of edges? Like what can they not do? Let's look at this scenario here. Take a vertex here and imagine x sends an edge to this z and y sends an edge to this z. That's a triangle. That can't happen, right? So every vertex over here, every z, it sends at most 1 edge to x and y. It can't send an edge to both x and both y. Okay, so z can't send edges to x and y. Otherwise, there's a triangle. Okay. So that means number of, let's say, cross edges is at most n minus 2. For every one of the n minus 2 vertices in here, there's at most one edge going to x and y. Maybe 0, but definitely not 2 ever. Okay. So that means that the total number of edges in G is at most, well, what? The edge x plus y, so 1 plus the edges going across from here, at most n minus 2, plus the number of edges by induction inside of G minus xy, which is n minus 2 over 4 squared. If you do the arithmetic here, you get n squared over 4. And that's the end of the proof. Because, like I said, you can round this down to the floor for free. If you're upper bounded by n squared over 4, then you're upper bounded by its rounding down, because e of g is necessarily an integer. Okay, so I mean, you can add another line of the proof to like make sure you can put the floor there. But that was nice, is like the floor thing didn't come from any like computation. It's just automatic. Okay. All right, so simple proof there. We use triangle freeness when applying induction and when counting the edges across. Okay. All right, so let's do some proofs that don't involve induction, although have some of the same ideas hiding in the background. Okay, so this triangle freeness can be observed in a number of different fashions. Okay. All right, so the first observation, okay, so we're starting over. So if G is triangle free, we're given G that is triangle free, then let's make the following observation. Then adjacent vertices, so vertices joined by an edge, don't have a common neighbor. We actually just observed that a moment ago. What's a common neighbor? If you have two vertices and they're both joined to a third vertex, that's x and y, this is their common neighbor, right? They have some neighbors and whatever's in common between them. But if x and y were joined by an edge, they can't have a common neighbor, right? Because that's literally the description of a triangle. We use that property above already, so we already proved that was possible. But so let's say otherwise, you get this thing here. Okay. Okay. So what does that mean? We can write this this description in a slightly different way from before. So this says, so for any edge, again, let's call it xy, we can add up the degrees of x and y. Okay, this is a little bit different. This is a little bit different from before. So before, let me just go up here. I counted the number of edges going from x to y over to here, right? We found that there were at most n minus 2 edges going across here. So if there's at most n minus 2 edges going from this side to this side here, what happens if I actually try to compute the degree of x and y? It's bounded above by what? Anybody see? Not n minus 2. Because if I compute the degree of this plus the degree of this, yes, indeed, the number of edges being counted that go across is at most n minus 2. But this edge should be counted by the degrees, right? Degree of x, this edge is contributed, and degree of y, this edge is contributed. So the sum of their degrees is at most n, right? 1 plus 1 plus at most, okay, this is insane notation, but okay, you see what I'm getting at here. You get 1 from each of these, and then at most n minus 2 going across there. So this sum for any edge, if you add up the 2 degrees, it's always at most n in a triangle-free graph. In other graphs, it can be much larger, right? Imagine a complete graph, dx plus dy is 2 times n minus 1, right? The two vertices. And no, actually, no, I'm sorry. It's even 2 times n. Yeah, 2 times n minus 1, of course, right? Each vertex has a degree n minus 1. But in a triangle-free graph, you get this. Okay, so let's take this inequality and sum it over every single possible edge in the graph. Okay, so let's write out this thing here. So for every edge xy in G, let's compute d of x plus d of y. Okay, so let me put this in hard braces here. All right, we know this is true for every xy that's an edge, so just compute the sum over everything. So this is bounded above by what? If I'm summing this inequality over every edge, n comes out every single time times the number of edges. Right, that's the number of terms in the sum is the number of edges, and each term in the sum, dx plus dy, is bounded above by n. And it's just, so summing over all edges gives this, okay? But there's a really cool way that we can rewrite this sum here. This sum is over all the edges of the graph. I want to rewrite this sum in such a way that it's over every vertex of the graph and has something to do with degrees. So let's think for a little bit here about what's going on. Think about this sum here, and imagine we're looking at vertex z. Okay, so just grab a random vertex in the graph and think about what happens here. D of z appears in this sum every time z is a part of an edge. Okay, so like if you have d of z here, it's got these edges on it. And for each one of these edges, the d of z and d of the other side will appear in this sum here. So how many times does d of z appear when say I wrote this whole sum out and didn't combine like terms yet, right? Just wrote them all out. For every edge, dx plus dy. For another edge, dx plus dy, and so on and so forth. Then for just an arbitrary vertex z, how many times does dz appear? Does anybody see it in this complete sum here?
It's either dz or 2dz.
Close, Ethan. So it appears as many times as there's an edge hitting z. So dz appears dz times, once for every edge, right? So it's we changed the name to x. So dx squared, right? dx appears dx times. So like this is a cool inequality. I mean equality, right? Summing the degrees on endpoints of an edge over all edges is the same as summing the squares of the degrees. Okay, now this is a good thing to see because this at least reminds us of the handshaking lemma, right? The handshaking lemma says if you add the degrees, you get 2 times the number of edges, which would be good. But here I'm not adding the degrees, I'm adding the squares of the degrees, okay? Anybody know, this is actually goes back to calculus again, how can you transform the sum of squares into the sum of the things originally? Somehow, it's not going to be exactly that, but there's an important relationship. Okay, anybody remember? It's a very famous inequality. It's more general than what we'll use here, but what's your, oh, Jose's got it. All right, yeah, very good. Cauchy-Schwarz, yeah, exactly. So now by Cauchy-Schwarz, I'm going to even put it Bunyakovsky. I hope your analysis teachers have talked about this, though it was discovered independently. Very, very often there's a Russian mathematician who did the same stuff as well. There wasn't a lot of communication in some of these eras. So anyway, a friend of mine likes to call this the BS inequality instead of CS anyway. So there's actually very interesting history of attribution for this inequality here. Okay, so Cauchy-Schwarz, Bunyakovsky says, well, I'll put its consequence for us here. So it says if you have the squares here, it's bounded above by 1 over n. N is the number of terms in the sum here, times the non-squared terms, all squared. Okay, this holds more generally. It doesn't have to be for degree. It can be any concave function.
Did you mean bounded above or below? Because I think you wrote bounded below.
This is bounded below. There are other versions depending on the function here that can be bounded above. So this should be bounded below.
Okay.
Let me think for a second here. Yeah. So and this is pretty easy to derive. I mean like the Cauchy-Schwarz inequality in general, but I don't want to go through it. It's look it up in your analysis textbook. It's proved in much more general forms as well. But just for a simple function, you can get this. Okay. This also is related to something called Jensen's inequality, which can be used here as well, which is a very common tool. Okay, so putting these things together, we have that this guy here, I'm just going to pull everything together, is bounded below by this and bounded above by this. So I'm just going to pull those two together. So I've got 1 over n sum of dx squared. This is over the sum of all the vertices of G. And then this is bounded above by n times the number of edges of G. That's just putting those two things together with this guy who's in the middle, right? Okay, so now this, we can apply the handshaking lemma to. Yes, there's a square here, but it's outside. The sum of the degrees squared. So I have 1 over n times the sum of the degrees squared the sum of the degrees is 2 times the number of edges of G squared. And this is at most n times the number of edges of G. And look what happens when you solve this inequality. You get n squared on the right side here. This 4 squared goes on divided here. And then I have number of edges squared, number of edges here. So divide by both sides by number of edges, which at some point we should have assumed was non-zero to perform this operation, but we did that in the previous theorem safely. So E of G is at most that, and we're done. Okay, so we apply Cauchy-Schwarz to get this proof here. It's kind of cool. All right, let's do another proof. Yeah, so the main idea in this, the whole idea in this proof was, yes, you do have to use Cauchy-Schwarz, but the important observation was this one here, that the sum of the degrees, this is where we use triangle freeness, right? Everywhere else was just either analysis or the handshaking lemma, right? I would say this is a key observation as well. But this is just a property of like summations. Okay. All right. So proof number 3. We'll use another inequality here, not Cauchy-Schwarz, something else, something even simpler, although you don't technically need it. Okay. This proof's really cool. Okay. So again, G is triangle free. So before we use the triangle free property to show that an edge never had a common neighbor, right? Otherwise that's a triangle. Now I'm going to look at this kind of from the opposite side, okay? So if G is triangle free, then the neighborhood of a vertex is an independent set. So take a vertex, its neighborhood is all the vertices that are adjacent to it, right? So these are all the vertices joined to X by an edge. And that neighborhood is independent, right? If I have an edge, oh, why is that not red? If I have an edge in here, then that's a triangle. That's 2 vertices whose common neighbor is X, right? X goes to everything here. So if there's an edge there, you have a problem, okay? So the neighborhood of a vertex is an independent set. There's no edges seen inside of there, okay? So now we're going to do something here. We're going to say, so let A be a max size independent set in G. Okay, G is our triangle free graph. Let's grab a large independent set. We don't need this for the proof, but this means that alpha of G is the size of A is alpha of G, right? That's what we know there's a maximum size independent set. Let A be it. And look at the picture here. So here's A. And then B is the remaining vertices. So A here is the largest independent set, and B is the rest. Okay, so and B is remaining vertices. Okay, so 2 quick observations. The degree of any vertex X is at most A, right? An independent, the neighborhood of a vertex is an independent set. So you can't have any vertex with more degrees than the largest independent set, right? It gives rise to an independent set. The biggest one, yeah. This bounds, so I can say for all X vertex. In other words, the maximum degree of the graph is bounded above by A, of course. That's the first observation. The second observation is every vertex has at least one end, sorry, not every vertex, every edge has at least one vertex in B, right? That's by the same reason. Every single edge in the graph, how does it look? It's either inside of B or it goes across from B. There's no edges inside of A because it's an independent set, right? This is not important either in this proof, but this actually means B is an edge cover, right? Maybe not a minimal one, but it's an edge cover, right? Every edge is seen by a vertex of B. Okay? We don't actually need that property, but okay. So this means, so we can estimate the number of edges of G as follows. The number of edges of G is at most, let's compute the sum of degrees, but let's do it in the following way. Let's only sum degrees of vertices in B, okay? So if I take a vertex in B and add its degree, then this is an upper bound on the number of edges. Why? Well, this vertex here, if I count the edges on it, the edges that go across are counted once in the sum. The edges inside of here are going to be counted twice, once for this end vertex, once for this end vertex. So this is definitely an upper bound, right? Some vertices are getting counted, overcounted multiple times. Some are getting counted once. Although in principle, B might be independent as well. And then every edge is counted exactly once. But the point is, this is just simply an upper bound, right? Every edge is counted at least once, maybe twice. But that's fine. It gives an upper bound on the number of edges. Okay? But now, every vertex, d of x, has size at most a, regardless of whether it sends edges to a or inside of b. Every degree is bounded above by a. And there's b terms in this sum. So this sum is bounded above by b times a. Right? B terms, each of which is at most a. And we've seen this little quantity before. What's the size of n at a plus the size of b? It's n. It's all of our vertices, right? All of our vertices are either in a or in b. So this is bounded above by, well, okay, let's say this instead. Let's just use the arithmetic geometric mean inequality. We don't have to use it here, but this is bounded above by b plus a over 2, well, over 4, sorry, squared, right? If you, what am I trying to say here? So, how do I want to rewrite this? This is, yeah. So AGM says that the arithmetic mean, okay, it's reworked, is an upper bound on the geometric mean. What's the geometric mean? It's this plus this square rooted. So I square both sides. And this would be, the arithmetic mean is this plus this over 2. So I square both sides and get this form here, okay? So AGM inequality, but you don't even actually need that because, okay, so let me just finish here. So AGM inequality says this, and then what's size of B plus size of A? That's n. All the vertices are in A or B. So this is n squared over 4, and that ends the proof there, okay? But you don't have to use AGM if you don't want to. If you just look at this quantity here and say, how big can that be? Well, A equals n minus B. So you're just maximizing the quantity B times n minus B. That's maximized at n half and n half by calculus, right? You can prove that by calculus directly. But I think it's cute to be able to apply AGM inequality, which can be proved via calculus as well, although you don't have to, you can even just use a regular arithmetic. Okay. Okay, so that's proof number 3. This one's fantastic. And actually this one can be adapted to prove the stronger theorem, to prove that, hey, the only way you get equality in all these things, so actually reaching this, is if every single vertex here sends all of its edges across and doesn't send them in here, right? Once I send them in here, this becomes a strict inequality, if you think about it for a moment. So if I don't want strict inequality, but equality, you never have an edge inside of there. So it says every vertex of B goes across to A. So then it says, great, it's a complete bipartite graph, actually. And then if it's a complete bipartite graph, in order to achieve this many edges, it needs both sides to have the same amount, basically n over half floor and ceiling. And so this, fiddling with this proof, actually gives the full statement that that construction is unique. There's no other way to achieve this many edges except for in that complete bipartite graph, which is cool. That's like an extra piece of information. Okay. All right, but that's just talking that one out. All right, so we do have enough time to do the 4th proof here, which is completely wild. Proof 4. This is by Moltken and Strauss in 65. The other proofs are kind of folklore. Like I don't even know if it's known who came up with these proofs. They're just kind of like been out there. I think I don't even know which one's Mantel's original proof. But Moltken Strauss is a totally different strategy, and is useful for, you can prove other stuff with it as well. Okay, so Moltken Strauss says the following thing here, and I'll run an example at the same time. So we have this very simple triangle free graph here, just a C4 at the same time, and I'll explain what's going on via this example as well. Okay, so what we're going to do is we've got G and it's triangle free and has n vertices. So G triangle free, n vertices, and I'm going to assign a weight function to every vertex. Okay, assign a weight, let's even say a non-negative weight Wx to each vertex x such that the sum of the weights on all the vertices adds up to 1, okay? So I assign these small epsilons to each vertex of the graph so that the total sum of those things adds up to 1. So like in this example, it could do like 1/2 plus 1/6 plus 1/6 plus 1/6 or something. That's a valid assignment. Does that make sense? Just as long as they're non-negative, they can even be 0. Okay, as long as they're non-negative and add up to 1, that's a valid assignment. Okay, and then I want to estimate. Let's estimate. So we're going to bound it above and below the following result of that function here. So S, and S is the following: sum up over every edge xy the product of wx times wy. Okay, so look at every edge in the graph, look at the weights on both endpoints, multiply them together and just add it up for the whole thing. I haven't done this in advance, but for this example up here, what would you get? You'd get on this edge, you'd sum up the product of those two, you get 1/12, and then you get another 1/12, and then you get a 1/36, and then you get a 1/36. Okay, that's the value of S for this graph with this specific assignment of weights. Okay, does that make sense? It's kind of an arcane function, but it's well defined. It makes perfect sense here. And what I want to do now is estimate the biggest that S could be. Okay, so estimate max possible S over all valid weight functions. Okay, obviously there's infinitely many ways to assign weight that satisfy this, right? I mean, it's a real valued function. It can take on any numbers. It just has to add up to 1, and you can't use negative numbers. Infinitely many ways to do it. But for any different way of doing that, this function here takes on different values, and we just want to know what's the biggest we can make it. What's like the smartest way to assign weights? Okay. Now, obviously, that depends on the structure of the graph very much, right? Like, if I gave you a different graph here and a different assignment, you're going to get a wildly different value. Okay? But let's figure this out. Okay. So first, assign Wx equals 1 over n for all vertices. Okay. That's the first version of this weight function we're going to do. I can assign 1 over n to every vertex. That's non-negative, and that obviously adds up to 1. There's n vertices. 1 over n times n is 1. Okay, which gives that S. Okay, so which gives max possible S here. So if I had given a specific assignment of values and then compute this function here, that gives a lower bound on the biggest S could be, because I gave you a valid quantity S could take on, but maybe there's a better assignment that's even bigger, right? So an actual assignment and then a computation is a lower bound on the maximum of S. And this is lower bounded by, well, what do the terms in this sum look like in this specific assignment? For every edge, compute Wx, Wy. Well, Wx, Wy is just 1 over n squared, because both of these take on 1 over n. And so the terms in the sum are identical, and there's E of g many terms in the sum. So the maximum this value can take on is certainly at least as large as E of g times 1 over n squared, right? That's literally what the value of this takes on in this specific instance here, okay? And so now, in order to prove the theorem, all I need to show, so this part's want to show, is that this is bounded above by 1/4. So concrete quantity, right? Everybody see, if I can show this, then solve the inequality for E of g, multiply both sides by n squared. I get number of edges is bounded above by n squared over 4, which is Mantel's theorem. Okay. So as of now we haven't done anything with triangle freeness, right? That comes out at the very end of the proof here. We just set up this function here. And now I want to say that no matter how smart I am with assigning values, I'm never going to exceed 1/4 when I do this function. Okay. So why should that be? All right, so what we're going to do, let me go back to the example here. What I'm going to do here, and I'll convince you of this numerically in a moment, is that if you look at this picture here and you say, hey, take two non-adjacent vertices. Okay, so two vertices that are non-adjacent, it's better in this picture to delete this value, put a 0 there, and increase this by the amount I deleted. Okay, and change this to 2/6. I'll convince you of that in a moment. Okay, so it's if I take non-adjacent vertices, it's better to 0 one out and then increase this to 2/6, and the total weight of this s function will not decrease under this operation. Okay, we can check this one real quick if we want. I actually haven't done it, so like maybe it's worth doing real quick. So here we get 0 and 0, so some things become 0, and now I get what do I get? 1/6 plus 2/36. So I actually get the same value in this case, right? If you know, it didn't decrease, which is all I want to prove. But this shifting, turning this to 0 and increasing this by the amount, didn't decrease s. Okay, so I'm gonna prove in just a moment that that's okay, and then we're gonna do it as many times as we can. And notice that shifting does not violate this quantity here. I lost 1/6 and gained 1/6. So the sum over all vertices remained 1. Okay, that's important, right? You can't change this function. Okay, so that's called like the weight shifting technique. Okay, so let x and y be non-adjacent vertices, and then we're going to compute big W sub x. So that's not the weight of x. This is equal to sum of weights on neighbors of x. Okay, so in other words, W of x is just simply the weight of z, where zx is an edge of G. Okay, that's what big WX is. So like again, like let me draw a different picture here. If this is x, then big WX is WA plus WB plus WC. Okay, it's just the sum of those things. And big W sub y is the same for y. It's the sum of the neighbors on those things. Now, when I look at this quantity, okay, that's maybe the wrong letters to look at. When I look at S, what does S look like? You write out the full sum of S, and the weight of x, Wx, will be multiplied by WA, WB, WC. Those will all appear in the sum. So if you write out the sum, we see the following terms. We see Wx times big Wx and Wy times big Wy. Those appear when you combine up all the like terms, right? All the things multiplied by Wx is literally this, and all the things multiplied by Wy is literally this. Okay. Now, without loss of generality, we can say that Wx is greater than or equal to Wy. They're just two quantities. One of them is bigger, or at least as large as the other one. Okay. Now, make the following observation. So here's x, and here's y. And x has these neighbors down here, y has these neighbors down here. They might even share vertices with neighbors with each other, but crucially, there's no edge here. Okay. Now, the weight on these things here exceeds, or is at least as large, the weight on these guys here, right? This is big Wx and this is big Wy, and it's like that. So what I'm going to say here is, let's zero out the weight here. So Wy, let's turn that to 0 and add to Wx, Wy. Okay, that's the shifting property I'm going to do. I'm going to zero out this, turn this to 0, and move the weight over to x instead. My weight function is still valid. Sum of all the weights on individual vertices adds up to 1 because I lost Wy and added Wy. But notice that what does this do to the new s? Well, now, so let's Wx plus Wy. That's the new weight on vertex x. That's times big Wx. Plus, what's the new weight on Wy? Well, I'm going to write it out here to illustrate, but it's Wy minus Wy, right, 0, times big Wy. But this is greater than or equal to the original. This is what we had originally, Wx times big Wx plus Wy times big Wy. Yeah. Right? We see this term and this term in our sum. So we see literally this term in our sum when we put everything together, these two things. And now this is what I've written above here is even bigger. When I shifted this weight over, I did better. You can maybe see it better by the illustration. Think of what happens in the sum. I have wy times each of these things and wx times each of these things. But I'd rather multiply wx and wy by these things than wy by these things, because the big wx is, there's more there. It's a better operation to multiply by. Okay? So this shift of weight from y to x cannot decrease s. Okay? It's crucial here that wx and wy are not adjacent to each other. Okay? If they're adjacent to each other, this observation doesn't hold. What's the reason for that? Well, because if wx, big wx, includes the value of the weight on y, when I zero out y, that alters the value of wx, and maybe this inequality no longer holds there. Okay? So they have to be non-adjacent vertices when I swap. Okay? But so I can shift weight from one vertex to another vertex that's not adjacent to it. Okay? So I want to do that as often as I can, and let's look at the illustration again. So the first shift I did in this picture was shift everything off this to this one here. Okay? Is there another shift I can do in this picture? I can't shift any longer to this vertex, right? Because it's adjacent to everything with weight on it. But what if I shift from here up to here? So let's delete this one, turn that to 0, and shift this to 1/6 plus 1/2. That operation should also not decrease the total s value, right? That's what we proved here. Now I've got a 0 here and a 0 here. Can I shift any further in this picture? No, I've got weight on a vertex and weight on another vertex, and they're joined to each other by an edge. But this shifting property I can do all the way until I'm left with all the weight distributed on only 2 vertices. Okay. So all weight can be shifted to 2 vertices on an edge. This is because the graph is triangle free. If the graph had a triangle and I was shifting weight, I can't escape this triangle, right? Maybe there's some weight here that's non-zero, some weight here that's non-zero, and some weight here that's non-zero. Like I can't move z to x, I can't move z to y. Like I'd get stuck here. But because my graph has no triangle, I can shift everything down to 2 vertices at the end. Okay? Like everything that's not adjacent to this vertex can be shifted there. Everything that's not adjacent to this vertex can be shifted there. Every other vertex in the graph is not adjacent to x or to z, right? You can't be adjacent to both. Same thing we've seen a bunch of times. So every weight can be shifted to this one or to this one. Okay? And now we're basically at the end of the proof, because now I've shifted all the weight to 2 vertices. So the function s, this sum here, wx, wy, for x, y, and edge, just boils down to wx, wy, or let's say wa, wb, for the 2 vertices I shifted down to. Everything else was 0. So I'm just left with these 2 things here. And now, this is the biggest, right? So s is actually bounded above, or let's say bounded above by this after I've done the shifting all the weight to these 2 things. And now I have wa times wb, and I know that wa plus wb is what? What's wa plus wb? It's 1. Yes, all the weight has been shifted to those 2 vertices. So now I want to maximize the product of 2 numbers that add up to 1. When is that maximized? We can use AGM again or calculus. It's maximized when they're both equal to 1/2. So this is at most 1/4, right? 1/2 times 1/2 is at most 1/4. And that's what we wanted, right? S was bounded above by 1/4 and bounded below by e over n squared. So solve for e and you get that. And this is crazy, right? I mean, this is like this is a cool idea. This is like a Lagrangian technique. This works in other places in mathematics. But it's really, really cool here. And you can see how this Mantel's theorem is about more than graphs. Like you can talk about other structures, and a triangle is one of the simplest, incident structures in all of mathematics. It's 3 things that are all connected to each other somehow. And if you don't have that property, then you get very similar theorems, even in group theory and other places. Okay. All right, so let's stop there.